No. Okay, so session is being recorded. So let's go back. Okay, I think we're here. So let's get a pointer. Got it. Reminder that we are going to start numbering to give our functional groups the lowest numbering possible, right? And so in assigning the stereochemistry, you were asked whether it was 2R, 3R, 3S. Some persons may have gotten a bit thrown off by numbering incorrectly, but we start numbering from here. So we're going to look at the chiral carbons in turn, and we know that chirality, you have 4 different things attached to a carbon. When we are determining the stereochemistry, we know that the hydrogen needs to be towards the back. In the current orientation, the hydrogen is coming towards. How do this? We see this hatched line that indicates the bond between the oxygen and the carbon. So the OH bond is going behind. And even though we haven't shown the hydrogen explicitly, we know that it must be coming towards. Because if the other bonds are in the plane, the OH is going behind, the only option for the hydrogen is to be going towards. And what we can do is rotate this section here for the hydrogen to be going buds. So we redraw our skeleton first, and then we do a step-by-step rotation, shuffling the atoms so that they get in the correct position. So we move, we're going counterclockwise, we're moving to push the hydrogen going to the back. So if the hydrogen has gone to the back, it means that the OH would have come around and gone to this position. So in our rotation, hydrogen has moved to go to the back. The OH is now in the plane, and that means the methyl is left to come forward. So this CH3 is now here. It is now coming forward. And after we have rotated to get the hydrogen going to the back, then we're going to assign priorities to our groups using our CIP rules. We know that oxygen is going to have the greater atomic number, is going to be the first priority. This carbon and this carbon, we have to use the point of difference to work out which one is going to take precedence. And it's obviously going to be this carbon right here, because it has another carbon, 2 other carbons, attached to it, whereas this is just a CH3. So we've assigned priority to our groups, and then we look at the direction of rotation, going from 1 to 2 to 3, and we see that we're going clockwise, right? Just putting that little clock so you get a frame of reference. We're going clockwise, and clockwise means that it's going to be R at the 2 position. Are we following so far? I can't say anything. Can someone just, yes?
Yes, fine.
Okay,
yes, Miss.
all right, great. Okay, good. So that was the first part. We've assigned the stereochemistry at this carbon 2, so it's 2R. We go to the next chiral center. We are going to not have to do any rotation because the hydrogen is already pointing behind. Once again, how do we know that? We looked at this, we saw that the methyl is coming towards, and these 2 other bonds are in the plane, and even though the hydrogen is not shown in this line structure, it must be going behind. And we're going to do the same thing where we use our CIP rules to assign priority. We know that there are 3 carbons that we're looking at, and we look at the point of difference. This carbon is attached to only hydrogens. This carbon is attached to a carbon and 2 hydrogens, even though they're not shown. But this carbon attached to both another carbon and an oxygen, so it is going to take priority. So 1, 2, 3, we've ranked our groups in terms of priority. We look at the direction of our groups going from 1 to 2 to 3. We see that we're going counterclockwise. So if we have a clock, we're going in the opposite direction that the hands would normally go. And so carbon 3 is going to be the S stereochemistry, all right? And so you can anticipate questions like this, which is a mixture of different aspects of the course. So you won't get a question just on substitution or just on. As you see in this question, it has different components, but they're sort of separated, so you can get marks at each juncture. So we've identified a stereochemistry. So if you work that out, you have gotten that correct. And now we need to work back ways. We have the product. We need to work out what we could have started with. And we look, oh, jumping a little too fast. We look at our reaction conditions. So we need to know the reaction conditions that do our organic transformations. The first one is borane and alkaline hydrogen peroxide. So hydrogen peroxide with oxide in there. Someone raising their hand, I can't see. You can unmute and answer your question, ask your question, rather.
Yes, it's actually Tina Shay. Am I the only one having flashing across my screen?
You're having something flash, I don't know. Guys, are you having issues seeing the screen clearly?
I'm seeing clearly, miss.
Yeah, we can see it clearly.
Okay.
Oh,
Is it dependent on the device? Are you guys using laptops versus phones, or could that be the challenge?
I'm using a tablet.
I'm even low.
Are you far from your router, Tina Shay? Are you?
No.
Is that it? Or is the
No,
signal?
God. But
I am not
what
sure.
I'm just gonna sign out and come back in.
Right. Yes, that sometimes does help. And this is also being, so if you miss a little part, it will still, you can still get it. Okay. All right. So we're going through our reaction conditions. We remember that borane and alkaline hydrogen peroxide are used to form alcohols. Can someone tell me what type of addition does borane and alkaline hydrogen peroxide give us? Is it Markovnikov or it is anti-Markovnikov? All right, and so that's also important to not only know that it adds water across the double bond, but how it adds water. And then we look back at our other reaction conditions. Hydroxide by itself does not give an alcohol when reacting with alkenes. It could only give an alcohol if it was reacting with an alkyl halide. So we know that B cannot be an option in this particular question. So we've eliminated it. We know that mercury and acid and water does what? What sort of transformation have we seen mercury and acid and water doing? Anyone? I can't see Blackboard. I can't see if anyone's raising their hand. Yes, go ahead.
I think they
Nobody?
hydrate to form an enol followed by a
Right.
ketone.
Yes, but what does it hydrate? Could you repeat what it hydrates?
An alkene or alkane? I'm not sure. I think
Alkyne. Alkyne. Right. So that's the one with the triple bond.
Yes.
Right. So mercury and acid and water will convert an alkyne. So that's something that has a carbon-carbon triple bond to an enol and then a ketone. And so we know that that would not be suitable for this reaction here because we are not making a ketone and we don't have an alkyne as our starting material. So that is going to be eliminated. And what about option D? We have O3, Zn, and ACOH. What are those? What do those do? Feel free to go ahead.
Ozonolysis.
Ozonolysis. And what is ozonolysis? What's that? Ozonolysis, what does it do? What sort of transformation? Does it give us alcohols? Anyone? Or are you busy answering in the chat?
A carbonyl compound.
It breaks.
Yes, go ahead, both of you. Someone answered, continue. It breaks.
Breaks the double bond to form carbonyl compounds.
Right. So in ozonolysis, you are cleaving or breaking the double bond to form a carbonyl compound, and that's also not what we want. And so we know that we can eliminate 3 out of the 4 options just by using our knowledge of reagents and what they do. So right away we know that reaction A, condition A, is what we're going to have to use to give us our alcohol, right? And then the next thing to look at is, okay, we know that borane and alkaline hydrogen peroxide gives us an alcohol by anti-Markovnikov addition, and that is going to influence which alkene we select for our starting material. But there's some other things we need to do first. We need to count our carbons, right? So we see that we have this carbon chain here, 5 carbon chain and 6 for the methyl. If we look at options 2 and options 4, we see that we have more carbons than are in our product. And so then carbon 2 and carbon 4 are going to be eliminated from being considered. They could not give us our product. None of this reaction with borane is going to lose any carbons. And so 2 and 4 are out. So comparing 1 and 3, remember borane does anti-Markovnikov addition. So out of 1 and 3, look carefully, which one do you think is going to give us A by anti-Markovnikov addition?
1.
Why? Why do you say 1? Does someone want to help? She said 1 very confidently, so let's elaborate.
If the OH was attached to the alkene 3, it would be in the wrong rotation, because as we know in the anti-Markovnikov product, it goes to the less substituted carbon.
Right. So that's a good point. So in anti-Markovnikov addition, our OH goes to the less substituted member of the double bond. So if it was 3, our OH would have gone to this carbon out here, and that is not where it is in our product. So it means that 1 is going to be the one that gives us the product that we need, because we recognize that this undergoes anti-Markovnikov addition, right? So that was question 1. Let me stop sharing for a little bit and hop over into the chat to see what you guys and Marcel are talking about. Come on, computer. Oh, wow, 34 messages. Okay, are we following? Let me see. Okay, All right, good stuff. Marcel is keeping you all occupied. All right, great. So I'm going to go back to question 2. Are there any questions about question 1? Anything that wasn't quite clear as to why we did what we did? Anyone? We're okay with question 1? And if we got something like this on the course test, we'd all be fine, right? Silent means consent. Wonderful. What was the BH3 used for again? Glenda, BH3 is borane, and borane is used in the hydroboration, and that's a stepwise reaction. First, you add the boron to the less substituted carbon in the alkene, and then alkaline hydrogen peroxide replaces boron with the OH. So it's a 2-step process to put the OH on. All right, and I hope that clears it up a bit. Yeah. Oh, okay, great. So let me go back to yes, Marcel, but 1901 was like so long ago, you know. All right, let me go back to the thing. All right, so question 2, we're looking at the same alcohol, but we're looking at a different way to make it. This time we're starting with a carbonyl compound. We're going to do a Grignard reaction. Oh, the pointer. you're going to do a Grignard reaction, and we know that we need acidic workup for our Grignard reaction to give us our alcohol. And so you need to work out which of these compounds can react with methyl magnesium bromide to give us this alcohol. Once again, our strategy, we're going to number up our carbons and work out which one is suitable. There is a thing that we should recognize, that the correct starting material should have 1 carbon less than the product. Because if we're reacting this carbonyl compound with 1 carbon to give us this product here, it means that the carbonyl compound, should have had 1 less carbon. So that when we add it up, we get the 6 carbons in our reaction. So we're going to go through again, count the carbons that are present in our structures. So 6 carbons in our product. Compound 1 has 1 less, so that's okay. It is still under consideration. But compound 2 has 4 carbons. It is short, so it's not going to give us what we want. 4 and 1 does not make 6. Compound 2 is eliminated. Compound 3 is also eliminated. It has 6 carbons, right? So it already has 6 carbons. If we added the methyl magnesium bromide, we'd get 7. It is eliminated. And compound 4 has 5 carbons as well. So once again, 1 and 4, we are going to consider them and to see which one would give us our product. So where does the Grignard reagent react with in a carbonyl compound? Where is it going to react? How do we know? Anyone? How do you know where the Grignard is going to react? Is it going to react at one of these N carbons here? Is it just going to stick on there? How do we know where it's going to go?
Would it attack the carbon that's attached to the oxygen?
Yes, it would. Why do you think it would?
Because the carbon, it has a positive charge from its attachment to the oxygen. But I just think it's more electronegative than the Grignard reagent.
Well, okay, let's break that down. You're correct. It is going to be the carbon of the carbonyl group. So this question is also to familiarize you with line structures, because for some persons it's hard for them to recognize that there's a carbon right here. At each of these little junctures, there's a carbon. There's a carbon attached and some hydrogens. There's a carbon here. It's attached to oxygen, which is more electronegative. So it's going to make this carbon a delta positive. Similar scenario here. So all of our carbonyl carbon are going to be delta positive, therefore electrophilic. So any Grignard reaction that takes place is going to take place at these carbonyl carbons. And so that's how we're going to decide whether 1 or 4 is going to give us our product. If a CH3 comes and reacts at this carbon, you're going to be forming a bond while you are breaking a bond. Similarly, if a CH3 comes here, you're going to be forming a carbon-carbon bond while you're breaking this carbon-oxygen double bond to the alcohol. Which one is going to give us our alcohol? Which one do you think? Anyone? You sound like we're busy in the chat. Anyone wants to say?
Miss, they're all saying 4, so I assume.
Okay. They. I like how you kept it safe. They are all saying 4, not me, miss. They. Right. So let us see. It is indeed 4, because if we added a carbon here, it would mean that this carbon would have 2 methyls attached to it in the final product, and that's not the case. It has 1 methyl and a hydrogen. So carbon 4 is going to be the carbonyl compound that gives us the product that we want, right? All right, so was that okay? Were we able to figure that out? I'm going to assume silence means yes, miss. This one was so easy. Stop giving us such easy questions. All right, let us go to question 3. Everything going okay in the chat, Marcel? I can't see.
Mr. Brown, I'm just responding to your questions.
Okay.
Yeah.
Cool. Thanks. Okay, so question 3 is yet another way that we're trying to work out how to make this alcohol, but we're looking at a different reaction, or a slight different reaction, because it is also a Grignard reaction, but instead of reacting with a carbonyl compound, this time you have epoxides. And just like carbonyl compounds, epoxides are going to have carbons that are delta positive because they have oxygens attached to them. So you're going to have carbon being delta positive and this carbon being delta positive. So both carbons involved in the 3-membered ring of the epoxide, both of them are going to be delta positive. This compound 3, this epoxide, is symmetrical, right? So it doesn't matter where the reaction takes place, you get the same product. But for compounds 1 and 2, we realize that if the reaction took place here, you get a different product if the reaction took place here. Similarly for this one. How do we know which carbon of an epoxide a nucleophile is going to prefer to react with?
Miss, can you repeat?
I'm asking, we have epoxides, both carbons are delta positive, which means both carbons are electrophilic. Which carbon is the nucleophile going to prefer? Anyone?
Miss, is it the one that is less sterically hindered?
Yes. And what does that mean, sterically hindered?
The branches, they are not blocking the nucleophile.
Right. So sterically hindered means the one that is more accessible. And as he said, the one that is less branched and the one that is less blocked. So using one as an example, we see that this carbon here is more accessible. A nucleophile can approach it more readily than this carbon where it has to get between a methyl and a hydrogen. For this one, it only gets between 2 hydrogens. And we know that the methyl is going to be bigger and bulkier than a hydrogen atom. Similarly over here, to react with this carbon, you would get between 2 hydrogens. So the hydrogens are, let me see if I can. Let's try this. Aha. So just imagine the 2. Oh dear. Just imagine the 2 hydrogens are drawn out. Let's go back to a pointer, shall we? And the nucleophile needs to react with this carbon. It has to get between these 2 hydrogens, whereas if it wanted to access this carbon, it has to get between a hydrogen and an ethyl group. So we can see it's always going to be easier to access the less hindered carbon. All right, good. So in this one, it's kicked up a notch because you don't know which Grignard reagent you're going to need to react with which epoxide. And so you're going to have to do some sort of deduction, some sort of addition first to choose one of the Grignard reagents and then be able to work out which epoxide it's going to be. So one approach is to number your, we already know that this has 6 carbons, right? So let's look first with methyl magnesium bromide. It is a source of 1 carbon. So it is only giving 1 carbon more to our starting materials. We count up the carbons in this epoxide, 1, 2, 3. 3 and 1 does not make 6. we count up this epoxide, 4 and 1 also does not make 6. 4 and 1 doesn't make 6 again. So we know that methyl magnesium bromide cannot be our Grignard reagent. It wouldn't give us enough carbon atoms to give our product, no matter which one it reacted with. All of these two have 4 carbons, this has only 3. It means that the methyl magnesium bromide would not give us a 6 carbon product. So that is eliminated, all right? So counting your carbons can, surprisingly, it can give you a lot of answers without knowing the reactivity. Just by counting carbons, you can sort of narrow down your options and get closer to a right answer. So we know our Grignard reagent has to be the ethyl magnesium bromide. That's the only other option. And once again, we count carbons. We need to get 6 carbons. We have 2 coming from the ethyl magnesium bromide. We can look at our epoxides to see if we can eliminate any of them. Can we eliminate any of our epoxides right off the bat?
Yes, Miss, number 1.
Definitely. All right. So we know that 3 and 2 does not give us 6. So we can eliminate epoxide 1 right off the bat. And so we're just left with 2 options. And 2 options is good because you have a 50-50 chance of getting it right if you were to randomly guess. But we're not going to randomly guess. We are going to work it out using our knowledge of organic chemistry. So we have a 2-carbon nucleophile reacting with our 4-carbon electrophiles. Which one do you think would give us our product? Note, in our product, we need to have a carbon attached to oxygen, and we need to have 1 methyl here, and then we have this branching here. Which of the epoxides do we think would react to give us the compound that we want? Persons in the chat. Because remember, if our file comes, it's going to come at the least hindered carbon. So our nucleophile would come here, right? And if we're forming a bond between our nucleophile and this carbon, we need to be breaking a bond. Can I do this? Yes. We would be breaking a bond between carbon 1, oxygen. So it would mean that carbon 2 would have the OH on it. And not only would carbon have the OH on it, the Grignard would have been added to carbon 1. But in our product, we only have 1 methyl here. So out of our 2 options, compound 2 or compound 3, which one is going to give us the alcohol that we want?
Number 3.
Pardon?
Number 3.
Number 3, yes. Number 3 is the epoxide that's going to give us what we want. So let me see if I can draw arrows again. Our Grignard would come in here. No, let me do the other side. Where's the eraser? Okay. So our Grignard can come in here. And so we're forming a bond with this carbon and breaking a bond between carbon and oxygen. So oxygen takes those electrons. And so what we're going to end up with is that this carbon would have the OH on it, whereas this carbon would have all the carbons from the Grignard reagent. And so this is what will give us our product, where we have a carbon with a OH on it and a CH3 and a H, and then this carbon would have a methyl substituent here and an ethyl chain that gets added. So epoxide 3 is going to be our starting material. Right? Okay, let me, this is the weirdest thing. Let's keep Okay, let me check. That's a lot of activity in the chat. So are we okay with those first couple questions? Not just the answers, but how to approach, because I could give you back the same questions and just slightly change the compounds. But if you don't understand why we do what we do, then that's not going to be helpful. Are we following the process of how we work out our correct answers?
Yes.
Or is it right there? We're following? Okay, let me, yeah, most of you were saying, could we go over the mechanism for epoxide 3, Tamis? Okay, let me go back in and do that. Yeah, this is the weirdest experience to be sitting at my computer talking to myself. But so it is. All right, so let me get up a pen. So our nucleophile, can I write this well enough? Yeah. Oh, Father. I'm using my mouse, guys. Don't laugh at my handwriting or my mouse writing. Okay, magnesium. All right, so we know that our nucleophile is the Grignard reagent and that the carbon is the nucleophilic atom in our Grignard reagent. The carbon is more electronegative than the magnesium, so it is going to have the delta negative charge, whereas the magnesium is going to have the delta positive charge. And so it is a carbon that is going to be the nucleophile that reacts with the delta positive carbon of our epoxide. So the electrons are coming from the bond shared between the carbon and the magnesium. So electrons always come from bonds or directly from atoms. So we are forming a bond between carbon 3, labeled 3 here, and this carbon of our Grignard reagent. This carbon 3 already had 4 bonds before, so if we're forming a bond, we need to be breaking a bond, and the easiest bonds to break are the polarized bonds. So we're going to break this carbon-oxygen bond, and the more electronegative atom is going to take the electrons. In this example, it's the oxygen. And so now we formed an ethyl group attached to a carbon that has a methyl, which is what we have up here in this structure, and we now have a carbon attached to an oxygen, an H, and a CH3. And so that's our product. Is that a little bit clearer, Tamis?
Miss, could you write the product? I want to see.
Oh,
I can't.
the product is this up here. You mean with the carbons?
Yes, Miss.
Yeah, give me a whole heap of work to do it this mouse. Okay, let us try. I'm going to do it at the top. It's because I have to write big.
So it's actually the bond between the carbon and the magnesium that attacks the carbon that on the epoxide.
Yes, that's the source of electrons. Because remember, a nucleophile is giving electrons to an electrophile, and those electrons are found in the bond. Remember, carbon doesn't have lone pairs, so it's always giving electrons to that bond. All right, CH3.
Dr. Brown, if I could offer another explanation. They seem to understand from an inorganic perspective. All right, so guys, when you're learning 1901 last year, you learn about electronegativity and the difference in electronegativity and how that affects determine reactivity, right? Now, if you look on the position of magnesium in the periodic table and carbon, you would expect that carbon will be more electronegative than magnesium. And because of that, carbon will be more delta negative and would have more electron density. So that's why it comes from, so Dr. Brown has it as the ethyl group being more delta negative than the magnesium. So even though you see the bond is doing the attack, the electron density lies closer to the carbon center. That's why it can do the attack. That's why you see the carbon is adding 2 the epoxide and not the magnesium bromide. Okay, does that help?
Oh, here is my,
Yes, it does.
Okay,
thank you, Mark.
I'm muting my mic.
No, that's fine. I'm not laughing at you. I'm laughing at my artwork at the top. The person who asked about me drawing the product, does this help you see it a little more clearly now? Yes? No?
Yes, miss, because I couldn't really see before which carbon would be joined to which. So yeah.
Right. So when you break this bond, this is what you form, and then we know that this negatively charged oxygen will get a hydrogen from the acid, and that was our final product.
Yeah.
Right. Yes. All right. Okay. So let us go to the next one. All right. Question 4 now is a combination of two topics. It is a combination of substitution and then revision and elimination, and also a little bit of revision right here. So it's all mixed in one. So the first question you were asked, you're given this scheme. So you look at your alkyl halide B and you look at your reagent. Cn minus is cyanide, and we have DMSO, which is a solvent. What kind of solvent is DMSO? How do we classify DMSO? Yes.
Non-polar.
Polar
Is it not?
aprotic.
Polar aprotic.
Polar.
Let me see if I can use my awesome drawing skills to draw DMSO so we can see what it looks like. DMSO looks like acetone. Let me put it all the way over here. Except the middle carbon is replaced by a sulfur. Okay. All right, so this is DMSO. And so we see that we have we'd have polarized bonds in here. So it's a polar solvent, but it is aprotic. We know that protics, how do we distinguish between protic versus aprotic solvents? Could someone just answer that for me, please? How do we know when a solvent is protic versus aprotic? Because that's important to work out which mechanism is going to happen. What do you look for in protic versus aprotic?
Hydrogen.
And what about the hydrogen? We have some hydrogens here.
Yeah. Protic solvents can go ahead. Protic solvents can form hydrogen bonds because of the
they can form hydrogen bonds. Also something else. Where's the hydrogen attached in a protic solvent?
Yeah.
Which atom is it normally attached?
The more electronegative element.
Right. So, and in particular, it's usually oxygen or hydrogen. So let me just quickly try and put up a protic solvent for an example. So, so this is supposed to be the Lewis structure for methanol, which is a polar protic solvent. And we see that in methanol, the hydrogen is attached directly to the oxygen, right? So in our protic solvents, the hydrogen is attached directly to an oxygen or a nitrogen, and that is why, as he said, it can undergo hydrogen bonding, right? So this would have been a polar protic, and this is a polar aprotic. So now that we've decided that DMSO is a polar aprotic and we have cyan in there, how do we use that information to find out if it is SN1 or SN2? How does solvent play a role in SN1 versus SN2? How does the nucleophile play a role in SN1 versus SN2?
If if the solvent is protic, then it will more likely to undergo SN1 as well.
Right. So protic solvents help to stabilize the carbocation, so you're more likely to have SN1, whereas polar aprotic, you're more likely to have SN2, because if it's polar aprotic, it makes the nucleophile better able to access or electrophilic carbon. What about, can anyone say, how does a nucleophile, cyanide, what kind of nucleophile is cyanide? Is it poor? Is it good? What is it? Oh, is there anyone? Okay, you guys are in the chat. Does anyone want to answer? Because I can't see anything in the chat. I can only see my PowerPoint screen.
It's good. It's a good.
It's a good nucleophile. Why? What kind of gave you a clue that it was a good nucleophile?
It has a localized negative charge.
Right. So the negative charge is localized, and in particular, it's localized on something that's not very electronegative, right? Which happens to be a carbon. And so cyanide is going to be a very good nucleophile, and it's a good nucleophile in a polar aprotic solvent. So which mechanism are we expecting this reaction? Because this is a secondary alkyl halide. It could go either way. Which one are we expecting it to go by?
SN2.
SN2. It's going to be an SN2. Ooh, sorry. Going to be an SN2 mechanism. Oh, right. So it's going to be an SN2 mechanism, and then it asks compound C. So compound C is going to be the product when cyanide reacts with alkyl halide B, and we're asking for the stereochemistry of compound C. Is it going to be the R isomer only, the S isomer only, or a mixture of R and S? Well, we can eliminate one of them right away. Which one can we eliminate?
The mixture.
The mixture, because we know it's not going by SN1. So because it's not going by SN1, then we know that this is eliminated right away. To work out which one is the answer with the R or S, we need to know the stereochemistry of alkyl halide B. Oh, and just to mention, originally in the quiz, I had set the incorrect answer. I went back in and fixed that. So you may say that your score has adjusted. All right, I had the incorrect answer originally. So let's work out the stereochemistry for alkyl halide B. We know that with SN2, we have inversion of stereochemistry. So if we know what the stereochemistry is for the starting material, then we know that compound C should have the opposite stereochemistry in this particular example. So bromine is going to take priority, then this carbon, then the methyl is last. And even though it's not shown, we know that there's a hydrogen going behind, right? Because if this is coming forward and these two are in the plane, then the hydrogen must be going behind. So we don't need to do any rotation. Going from 1 to 2 to 3, we are going in an anti-clockwise movement, and so it is going to be the S isomer. So if B was the S isomer, we should have inversion of stereochemistry. And so compound C is going to be this product here. Notice that bromine was coming towards us. Cyanide would have attacked from the opposite face. And so the cyanide is now going behind. And let's work out the stereochemistry here. We want to rotate it so that hydrogen is behind. And we assign priority to our groups, and we have the R isomer, right? And so that should be the answer. It's going to be an SN2 reaction. This S isomer is going to be converted to the R isomer. Is this part clear to everyone? The steps that we took to work out that it was SN2. Notice we had to use clues. We had to use the solvent. We had to use the nucleophile to work out whether it was SN1 versus SN2. Then we had to recall that with SN2 mechanism, you have inversion of stereochemistry. So what was coming towards you, the incoming group is going to be going behind, and then we see that it's now the R the R isomer. Was this part of question 4 okay? Okay. All right, so the last part of question 4, or the second to last part of question 4, it's asking how you can convert an alkyl halide to this particular alkene. When we look at alkyl halide B, we know that elimination could give you two possible products. You could lose a hydrogen here, so the double bond is between this carbon and this carbon, or you could lose a hydrogen here, and the double bond is between here. So in this one, you have two substituents on your double bond, so substituent 1, substituent 2, versus this one that you have only one substituent. So this is the least substituted alkene that is formed in our reaction. And what is the name that we give to the least substituted alkene? Anyone want to type that in the chat or say it? The least substituted alkene, there's a particular name we use to refer to it.
The Hoffman.
The Hoffman, right. So we need to know which reaction conditions are going to give us the Hoffman product, and these are the options that we have. All of these are bases. So it's hydroxide in DMSO, or ethoxide in ethanol, or hydroxide in ethanol, or tert-butoxide in DMSO. Which of these conditions here is going to favor the formation of the Hoffman product, the least substituted alkene? Anyone?
A bulky base.
A bulky base. All right, good. Now, which of these is going to be a bulky base?
Tert-butoxide.
The tert-butoxide, right? So tert-butoxide of all of these is the bulkiest base. And so it is going to favor elimination to give us or less substituted alkene. So the answer is the tert-butoxide, and DMSO is going to give us the less substituted product, right? And to get elimination over substitution, you also need your base to be non-nucleophilic. So it couldn't have been hydroxide, because hydroxide could have just replaced the Br and you got an alcohol instead. So this last part comes from 1901. We have an alkene, we treat it with ozone, followed by hydrogen peroxide. So this second part is important. Tells us something. Ozone followed by hydrogen peroxide means that we're going to cleave this double bond. So it means that this part is going to be snipped off, right? And so out of all the options, let me go to that slide. Oh, the answer was there. Out of all the options, what do we get? Let me number 1, 2, 3, 4. So if we have ozonolysis with this alkene followed by hydrogen peroxide, compound D is going to be what? Anybody? What does hydrogen peroxide do? Why is it?
Would it be pentanol, like a primary alcohol?
No, because we're cutting. Remember, for ozonolysis, we cut the double bond, and wherever the double bond is, we replace it with oxygen, right? And so we're let me rub out this line. Rub out this line. So wherever the double bond is, we replace it with an oxygen, and we know we'd have had an hydrogen here. Let me draw that out. But then the hydrogen peroxide is important. There's a hydrogen here, even though it's not drawn in the structure. Jesus, hold on. Let me do this, Anita. So there's a hydrogen here. What's the role of the hydrogen peroxide? So ozonolysis cleaves this double bond, and now instead of having a 5-carbon alkene, we have a 1, 2, 3, 4-carbon carbonyl compound. That's the after ozonolysis. And after hydrogen peroxide, what happens to this structure? Are there any changes to the structure? All right, you guys are busy answering in the chat. Hydrogen peroxide, we know, is an oxidizing agent. So ozonolysis is going to cleave it first to give us our aldehyde, and then our aldehyde undergoes further oxidation with the hydrogen peroxide to give us our carboxylic acid. So you'd have gotten two aldehydes here, a 4-carbon aldehyde and a 1-carbon aldehyde. And I've just used the same numbering. So you see that all of these carbons in this aldehyde came from 2, 3, 4, 5 in the alkene, and the carbon in this aldehyde came from carbon 1. And so we have a 4-carbon carboxylic acid after oxidation with hydrogen peroxide, whereas for this methanol, it would be oxidized up to carbon dioxide. And so compound D is going to be butanoic acid, right? Because our aldehyde that's originally formed after ozonolysis undergoes oxidation to give us our carboxylic acid. Is that part clear to you?
Yes,
Yes,
miss.
miss.
Yeah, you're okay. All right, good. All right. All right, question 5. We're looking at carbonyl chemistry and its reaction with nucleophiles. So we know that in this reaction, this carbon is going to be the electrophile. Remember, our carbon is attached to our electronegative oxygen. And in this one, our nitrogen is going to be the nucleophile because we know that there are lone pairs on this nitrogen. And an imine has a C double bond N. So imine has a C double bond N, right? And so it tells you that an imine is formed. And so in any of your options, you should have a C double bond N. And the nitrogen that reacts with our carbonyl compound also has a CH3 attached to it. So in the imine, you should have a C double bond N CH3. Right? And so right away, see what product we're supposed to have, right? What's the answer for the imine? What structure does it have? Anyone? Which of the options has a C double bond N with a CH attached?
Option 2.
Option 2, right? So we're practicing our line structure again. This line, at the end of this line, we know that there's a CH3, right? So it can't be 1. And also 1 has a wrong number of carbons, so we can eliminate. It can't be 3 as well because this is not this carbon chain doesn't change. The reaction occurs all up at this point. So it can't be carbon 3. Option 3, sorry, it can't be option 4 as well because this is a C double bond C. It doesn't have a C double bond N. So it must be 2 that has a double bond N and still has a CH3 attached to the nitrogen. All right. Yeah. And so these notes, these slides are a PDF that have been posted. So you can look through those as well. All right, very quickly, time is winding down. These transformations, so here are our options. For question 1, I'm asking, you have butanone and you convert it to butane. It means we're moving from an ketone to an alkane. Out of these 3 options here, which one is it?
Wolff-Kishner.
Which one converts Wolff-Kishner? So we know Wolff-Kishner converts carbonyl compounds to alkanes. So, Wolff-Kishner it is. Let's just go through all of them. We're going from an alcohol to an aldehyde. Out of these 3 options for question 2, which one is going to convert an alcohol to an aldehyde?
Oxidation with PCC.
Oxidation with PCC. Clemenson would not do it. Ozonolysis does not react with alcohol, so it must be oxidation with PCC. Now we're moving from an aldehyde to an alkane. Out of these 3 options, which one is going to give us what we want?
Clemenson.
Clemenson. So both Wolff-Kishner and Clemenson convert carbonyl compounds to alkanes, right? And then finally, we're moving alcohol to a ketone. Which condition is going to give us that?
Oxidation with the Jones reagent.
Oxidation. So moving from alcohol to ketone, it's going to give us oxidation. And so those are the reactions. So you need to know your reactions and the transformations that they do in order to be able to answer this question. All right, last thing. Yes, oh dear, it's 6 o'clock. Last thing, we're looking at reduction. So we have compound F. We want to know, how do we get rid of the double bond and leave the carbonyl to give you this compound in reaction 1? Or in reaction 2, how do we get rid of the carbonyl and leave the double bond? So reaction 1, how do we reduce a double bond to give us an alkane without troubling the carbonyl? Which combination should we use? There's some right away we know we can eliminate. We know we can eliminate ozonolysis because that cuts double bonds, it doesn't reduce them. We know that PCC is an oxidizing agent, same as Jones reagent, so those won't be doing what we want. So which one is it going to be that reduces a double bond but doesn't trouble the carbonyl?
Palladium with hydrogen.
All right, so it's going to be our transitional metal palladium and hydrogen that is going to reduce the double bond, but it's going to leave the carbonyl group unchanged. So that's for reaction 1. For reaction 2, we want to do, for reaction 2, do the opposite. We want to get rid of the carbonyl and leave the double bond. And so the reagent that's going to do it is hydrazine and hydroxide. It's not going to be the palladium. Sodium borohydride, what would sodium borohydride have done to the carbonyl group? Anybody? What does sodium borohydride do? What kind of reagent is it? Oxidizing? Is it reducing?
Sorry, reducing agents.
It's a reducing agent. It would reduce the ketone group to what?
OH.
To an OH. That's not what we want. So we know we can eliminate sodium borohydride. And of course, we can eliminate all of these oxidizing agents here. And so we're left with hydrazine. So N2H4 is hydrazine and hydroxide. And which reaction uses hydrazine and hydroxide? We just spoke about it a while ago.
Wolff-Kishner.
Wolff-Kishner, right, okay. All right, folks. Yep, let me jump back over. All right, so here we are. We went through the questions. As I said, this is being recorded, so you can look back at it. And also the slides are up as a PDF that you can look at it as well. If you did not get a chance to do the quiz, I would still ask you to do it. Just do it to see how was my internet connectivity while I was doing it. Was it dropping every minute? Am I able to do it well with my phone as well as with my laptop? Because, you know, sometimes stuff happens and you need to jump and use your phone. Oh, Sarah, for question 8 and 9, that's carried over to the other tutorial. So you're going to do that in this week's tutorial that's coming up. All right. Okay, folks, I think this has been a okay first session. Were most persons able to hear throughout the session? You could raise your hand and back over. You're able to hear. Okay, good. And you were able to stay connected throughout the whole time. Nobody was being kicked off. Okay. All right, good. I think with the smaller groups, Blackboard behaves better than with the larger group. All right, thank you guys for coming. Thank you for showing up to class. And thank you. Let's thank Marcel a lot for helping out. It would have been extremely difficult for me to monitor and answer your questions in the chat while doing what I was doing. So thank you very much, Marcel, for assisting. What you call it? Lab is up. The lab for next information is up. Those of you who are in the
Dr.
Monday.
Brown,
Yes, what's up, Marcel?
somebody put in a WhatsApp group that they're not able to see the lab. They're not seeing the lab being put up, so they were asking where is it that Dr. Simpson posted it.
It could be, no, we posted it directly. The students were put in groups. First of all, let me ask, has anybody seen it? Yes, okay.
Yes, miss. You have to like scroll down on Orvally until you find your specific lab stream.
Right. I think what happened is that that person is not in a group. Marcel, could you ask them to email me or to just tell you, whichever is easier for them, to tell you their name so we could place them in a group. We place students in the group, so everybody is seeing something slightly different. This is just to encourage independently.
Okay.
All of them. Right. So if they're
I'll
not
reach out to them
going to be able to see anything. All right, so we'll talk afterwards and we'll see how we can sort that situation out. All right, guys, the lab is up and you need to be reading and preparing. Monday's group, Monday morning at 9 o'clock, we'll be in a session to answer questions. So you need to do some prep before so we can get the most out of the session. All right, everyone, have a wonderful evening and I'm gonna stop recording now.